So now what we're going to do is we're going to look at some of our essential functions that we're going to be using when we're doing calculus. So the first is when we have what is called a linear function. So a linear function is just any graph that is linear, or a line, that is not a vertical line. So the most common forms you're going to see are going to be the slope-intercept form, which is just going to be y equals mx plus b, where m is the slope of the line, that's how much it's increasing, and b is our y-intercept. So if we were to kind of graph it like this, b would be where it's going to cross here, and then slope would determine how much is it increasing, right? Is it increasing by some amount? Is it increasing by more? Is it increasing by less? So this slope, you can think of, we usually call it rise over run, and this will tell you what the slope is. So whatever x value I plug in, it would be, starting at that starting point b, x times m would tell us where we end up to get all of our different y values. When we have more than one point, we may actually want to use what's called the point slope formula. So the point slope formula is just that we have y minus y1 equals m times x minus x1. In fact, we're going to be using this one a lot in this course. So basically what it's saying is that if I have some point x1, y1, and I know what the slope is because we're going to find that using derivatives, I can plug in x1 and y1 into this, and I can figure out what is the equation that represents this line that is the tangent at a specific point. And this will all make sense when we get to that when we're doing derivatives and stuff like that. The next kind of function we want to look at is called a polynomial function. So a polynomial function is just going to have the form, p for polynomial, is going to be an to the x to the n power plus a n minus 1 x to the n minus 1 power. And then we would do this going on and on, right? So this would become a n minus 2, x to the n minus 2. And we do this until we get down to, so plus a1, x to the 1, plus a 0. And what this means is basically a higher order function where if we were looking at our basic function, right, this would be if you have a single x, right, an x to the first power, so just in terms of x. This would be when you don't have x. This would be something like y equals 4. This would be y equals 2x plus 4. Then of course we have, what about square functions? You have, y equals 3x squared minus 2x plus 4, things like that. And pretty much a polynomial function can have up to n number of powers. This is just different powers. The numbers an through a1 are coefficients. So this would be the coefficient for your x values. This would be your coefficient for your x to the n values, or your nth power values. And n is the degree of the polynomial. So for example, if I have a cubic function, that means that I have terms in terms of x to the x cubed. This would mean that my n is equal to 3, because I would have some a3 x cubed plus a2 x squared plus a1 x1 plus a0. Which you can think of your a0 as your intercept, like when we were doing our linear function. Then there's your power functions. So a polynomial of the form f of x equals x to the p power is called a power function. That means it's being raised to some power p in this case. So it'd be like this polynomial function, except for all you have is whatever the highest power is. So if I had x cubed, then this would be a power function. It's a cubic function, right? It's cubing whatever value I put in. If I have p equals 1 over n, then this is called a root function. So what this means is I have f of x is equal to x to the 1 over n. This is the same thing as saying it is the nth root of x. This is something that's actually going to be used a lot in this course, because a lot of times we're going to have to deal with multiplying, adding, subtracting powers, things like that. And it's easier a lot of times to think of it in terms of its power function versus thinking of it in terms of a root. And then similarly, if we have f of x equals x to the negative 1, the way that this works is it ends up being equal to, sorry, this should be n, 1 over x to the n. So anytime you have a negative power, this is the same thing as doing 1 over x to the positive power. And again, these are all things we're going to use quite a bit. For example, if I had something like 1 over x to the 1/3, then this is actually equivalent to saying that I have 1 over the cube root of x. So this might be the form that you originally have whenever you're doing calculation. You can convert this to 1 over x to the 1/3, which then you can further convert this to x to the negative 1 over 3. And this makes it a lot easier to deal with certain things. For example, when we're learning about the power rule, this makes the derivative super easy. Can't really apply it on this one very well, but in this form, it actually becomes very easy to do. Next, we have rational functions. So a rational function is just a ratio of two polynomials. So that is, say, something like f of x is equal to px over qx, where in this case, qx cannot be equal to 0, because in that case, you would have 0 in the denominator of a fraction and doesn't really work out. We have our trigonometric functions, which would be things like sine, cosine, tangent, secant, cosecant, cotangent. And of course, we're not going to go deep into detail on those. We will use some when we're doing the course. But if you wanted to find out more, I would either look at a trigonometry course or book, or actually even some calculus books will actually have the trigonometric functions in the appendices. Next, we have exponential functions. So exponential functions are of the form, so sorry, this is a rational function. And then we have exponential functions, which is just going to be of the form f of x is equal to b to the x, where b is going to be your base, so, and b is positive for an exponential function. So basically, this would be your base, and you're now taking it to some x power. So notice usually we have x to a power. An exponential function is some value to some x value. Now, the reason that we're saying that x would need to be positive is because, remember, unless you're restricting this x, so for example, you could have x be, b be something different depending on if you have a very local interval, but what would happen if, for example, my b was equal to -2? And then my x, what happens if I put x to the -1? Well, this becomes, x to the 1/2. So if x is equal to the 1/2, then this would be -2 to the 1/2. Well, 1/2, if you remember from what we were just talking about, would be the same thing as saying this is the square root of -2. In which case, now we're dealing with complex numbers. So for most functions, then this would mean that this doesn't really work, which is why our b would need to be positive. Now here I put greater than or equal to. Now you might see actually a problem with this as well, right? And this is why you should always think about what it is that each of these things would represent. Because what if, again, b was equal to 0, and I had x is equal to -1. So then this would be 0 to the -1 power, which is the same thing as saying 1 over 0 to the 1 power. Well, 0 to the 1 power still would be 0. This really doesn't work. So really, this is actually just b is greater than, which is why specifically I said that it's positive, not greater than or equal to 0 or positive or equal to 0. So I actually did that on purpose. I just wanted to kind of show you kind of the thought process of when I make some random statement like that, b has to be a positive value, there is a reason for it. And if you kind of break down, okay, what would happen if I plug in a negative? What would happen if I plug in a 0? Then you can get a much better understanding of why these things would need to be true. Next, we have our logarithmic functions, which would be of the form f of x is equal to log bx, where again, b is our base, and it must be positive, greater than 0. Now that we've learned a little bit about functions, we're going to look specifically at translations of those functions. So let's say that you have some function f of x. What would happen if you were to add some constant to it? Well, in this case, what it's going to do is it's going to take whatever function you have and it's going to raise it up by c amount. For example, let's say that we have f of x plus 4. Well, remember, whenever you have f of x, you're going to be getting some outcome, right? So if I plug in a value and I get out 3, well, f of x would be 3. So let's say I plug in some x here and I get 3. Well, then this is telling it, okay, take that and raise it up another 4. And that's exactly what this would do. It would transition it up. If you have f of x minus c, this would take whatever function you have and it would shift it downward. Next, if we have inside of our function, so if we have f of x plus c within the function, this is actually going to cause us to move to the left. And this is because what we're doing is we're saying, okay, whatever value we had here, let's say this is equal to 4. If we had f of x is equal to 4, now f of x plus c is equal to 4 would mean that we are shifting the whole thing over to accommodate for that, right? So let's say that my original function was something like this. And if I wanted to say, okay, but I want x plus c to be also equal to 4, for this to be true, I would have to shift the entire thing by shifting it over to the left to make this true. Similarly, if I have x minus c, this is going to shift it to the right. Let's test this out to show this. Let's say that my f of x is just equal to x squared plus 2, right? Well, what would happen if I were to add c within this? Well, we'd have f of x plus c is equal to, now what happens? I take whatever's within the parentheses and I replace x with it. So this becomes x plus c squared plus 2. Of course, I'm going to FOIL this out. Just like before, this is going to end up giving me x squared plus 2xc plus c squared plus 2. Now again, if I had this equal to some value, what's going to happen is this is going to have to shift in order to account for this. Now let's test it out in action. Let's say that x is equal to 2. So this would end up being 2 squared is 4. 4 plus 2 equals 6. Well, this is going to be 2 squared is 4 plus 2 times, this would be 2 times 2c, so plus 2c plus c squared plus 2. So this would end up being 6 plus 2c plus c squared. Now, if I plug in, let's just make it 1 for c, this would end up being 6 plus 2 times 1 plus 1 equals 9. So what's happened? We've actually shifted to having a higher y value. So if I wanted to keep it equivalent, then what happened is the whole thing has to shift to the left, because now what's happening is that I have actually raised it so that it would need to be at the same sort of value, x equals 2. It would have to be shifted to the left to now be equal to the outcome of y that I had here, which was, in this case, 9, and this one was 6. This is not drawn to scale. Now let's talk about reflections of our function. If we have y equals, which y is just a way of saying a function, is negative f of x, this is going to reflect over the x-axis. Basically, whatever it's saying is whatever value I would have gotten that was positive, now I'm taking the negative of it, so I would get the negative. So if I had a value here and a value here, it would look like this. So instead of being like this, it now is going to be like this. I'm reflecting it across the x-axis. If I had y equals f of negative x, this is going to reflect over the y-axis, right? So this means that if I had some value here, this would be equivalent to flipping it over the y-axis. Again, this would be something like, if I just had, let's say f of x is just equal to x. So if I have f of x equals x, and I'm plugging in 4, so this would be equal to 4, So f of 4 equals 4. If I were to take the negative of that, so negative f of x, negative 4. So instead of it being equal to 4, it's now equal to negative 4. Vertical and horizontal stretching will move a graph so that it's closer to one of our axes. So for example, if we have y equals c times f of x, what this is going to do is this is going to vertically stretch, meaning it's going to stretch it in this direction. So if our original graph was something like this, what it's going to do is going to stretch it this way, meaning that it will be closer to our vertical axis. If we had y equals 1 over c times our function f of x, this is going to be kind of compressing it down, and it's going to cause vertical compression, meaning it's going to go further from our y-axis because it's going to take the same function and it's going to compress it down, right? So this would be 1 over c f of x. This is f of x. This was f of x, and this was c times f of x. What about if we have something within the function? So if we have y equals f of something multiplied by every x value, there's going to be horizontal compression, meaning that if I have my x and y axes, if I have some f of x, what's happening is it's taking this and it's compressing it in, meaning that it's going to be further from the horizontal axis. Similarly, if I have y equals f of 1 over cx, this is going to be horizontal stretching, which means that it would be something like this. If this is my f of x, just like this was f of x, this was f of cx, this is going to take this function and it's going to horizontally stretch it, meaning that it is going to be closer to the horizontal axis. You can actually combine functions together. So these combinations of functions are where we have two functions, f and g, and these can be composed into a new function. So this composite function, which is denoted as f of g of x, is really just you're taking the function of the function g of x. So you're taking g of x and then you're putting that into your f of x to get some new composite function, or think of it like a multi-step function. It's a function made up of two functions. So let's do a quick example on this. Let's say that we had f of x equals x squared plus 1, and g of x is equal to 2x plus 5. So if we're looking at f of g of x, then what this is going to be is this is going to be, we're going to take our g of x and we're going to plug in whatever g of x is, wherever we have an x. So this is going to be equal to 2x plus 5 squared plus 1. And then, of course, just like before, we're going to FOIL this out. So we're going to multiply the first terms. This is going to be 4x squared. We're going to do the outer and then the inner terms, which is going to be 2x times 5, which is going to be 10x. There's going to be two of them, so there's going to be 20x. And then the last terms, plus 25, and then, of course, plus 1. So this is just going to become 26. So this is going to be 4x squared plus 20x plus 26. And then if I wanted to, I could possibly simplify the fact that every single one of these has a 2. I could pull that 2 out and then make it a simpler function, depending on whatever I have on the other side of the equation. What about if we went the other direction? What if instead of f of g of x, we did g of f of x? Which, remember, is just the same thing in this case of g of f of x. So whatever we have as f of x, we're going to plug that into g of x. So we're going to take x squared plus 1, and we're going to plug it in here. So we have 2 times x squared plus 1 plus 5. And then this is going to be, I'm going to distribute the 2. So this is going to be 2x squared plus 2 plus 5, which would be 2x squared plus 7. In this example, we have table data for our x values when x equal to 1, 2, 3, 4, and 5. We have our function f of x when x is equal to 1, our f of x is equal to 5. When x is equal to 2, f of x is equal to 2. 3, 2, 4, 1, 5, 4. G of x is when x is equal to 1, g of x gives us 2. When x is equal to 2, g of x gives us 3. So now what we want to do is we want to see how does a composite function work when you have the outcomes of each of our functions. So in this case, let's say that we had f of g of 1. So what we're saying is this. We're basically saying f of g of 1. So g of 1 is what is g of x when x equals 1? Well, in this case, it's equal to 2. So this becomes f of 2. And f of 2 would be equal to 2. Right? Because it's what is it when x is equal to 2, f of 2 would give us 2. What about when we have g of f of 5? So again, this is g of f of 5. Well, when x is equal to 5, my f of x is equal to 4. So this would be g of 4. When x is equal to 4, my g of x would be equal to 5. What about if we had f of g of 2? So again, when x is equal to 2, g of x will be equal to 3. So this would be f of 3. And then when x is equal to 3, f of x would be equal to 2. And then last one, what about if we have g of f of 4? So f of 4, so when x is equal to 4, f of x is equal to 1, so g of 1. And this would be equal to, when x is equal to 1, you get 2. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.